Hello, I'm Dae-Young Kim from Soonchunhyang University of Korea. My colleague and I studied on pseudo-labeling and time series data analysis model for device status diagnostics in smart agriculture. And now I'm happy to introduce to our research. Smart agriculture leverages digital technologies to enhance efficiency, optimize resource use, and promote sustainable farming practices. By integrating IoT devices and data analytics, farmers and system developers can make informed, data-driven decisions to address various challenges. IoT devices monitor key environmental and operational variables. The result of this process is a vast amount of time series data that is critical to the creation of predictive models. However, given the sheer volume and complexity of time series data, a primary challenge in developing machine learning applications for smart agriculture is manual data labeling. This process is labor-intensive, time-consuming, and prone to inconsistencies, making efficient scaling difficult. So, in the proposed approach, the proposed algorithm extracts feature regions through waveform segmentation. The features are used by the machine learning model to classify and predict the operational status. The process is further automated by generating labels for new data based on learned features. By integrating pseudo-labeling with machine learning, the proposed method provides a significant improvement over traditional manual labeling techniques. Here, the pseudo-labeling means a supervised learning method that uses a small amount of labeled data to assign labels to the larger unlabeled data set. For machine learning-based fault diagnosis, the proposed approach utilizes waveform segmentation to analyze system status. This waveform segmentation divides time series data into temporally contiguous segments that help identify specific periods of operating conditions. This figure shows the semantic segmentation in time series data. Each segment represents a specific operational state that facilitates accurate fault classification. This visualization is particularly useful for understanding the structured approach applied to the fault diagnosis process. For machine learning, data preprocessing is needed. In our approach, we apply 3 steps of data preprocessing techniques. First, filtering signals. It can help remove unnecessary noise by selectively passing or blocking frequency bands, enabling neural networks to better discern the features of actual signals. Second, rescaling. Rescaling time series data for normalization is the process of transforming data to a new range, allowing the data distribution to be adjusted. And last, the FSST. FSST is Fourier synchro-squeezed transform. It is a mathematical tool for analyzing the dynamic characteristics of frequency modes in the frequency time domain of time series data. This figure shows the result of data preprocessing. The preprocessed data is used for machine learning inputs. In our approach, LSTM neural network models are utilized for waveform segmentation. This model generates output in the form of a sequence or mask in which each label corresponds to a segment of the input signal. In the proposed approach, processing long sequences of input data requires careful management to prevent performance degradation and excessive memory usage. Thus, input signals and their corresponding label masks are split into shorter segments. This figure shows our proposed model. This model facilitates the segmentation and classification of time series data collected from agricultural sensors to automate the labeling process. This figure shows our experimental data collection systems. This includes IoT-enabled sensors and control systems that continuously monitor soil conditions in real time to automate irrigation. The key components of the system include soil sensors, gateways, and data storage units, all of which support efficient environmental monitoring and data-driven decision-making. Our methodology has 3 steps for diagnosing sensor states. First, time series data collections. Time series data are collected from sensors installed on the smart palm. Data are collected for a year and segmented into 10-day intervals. Second, waveform segmentation and state extractions. The collected time series data are segmented using waveform segmentation techniques, and features are extracted from each segment. Machine learning models are trained on the extracted features to classify the operational states based on the time series data. And last, partial labeling of features. Initially, we manually labeled the specific sections where peaks appear during watering events. By leveraging this partially labeled data set, learning models automatically label the remaining data, significantly reducing the time and effort required for manual labelings. Our methodology introduces a novel pseudo-labeling technique to automate the labeling of semantic segments in the time series data. This process involves using machine learning algorithms to identify patterns within the data and assign the labels based on learned features, reducing the reliance on manual labeling. This figure illustrates the segmentation process. This figure provides examples of semantic segmentation based on predicted labels and shows how manual labeling can introduce errors. There are 2 types of errors: missing segments and inaccuracy. Missing segments. These occur when certain regions are overlooked during real-time data labeling. In case of inaccuracies, misclassification errors may arise from similarities between different classes, the ambiguity of real-time data, or the limitations of segmentation algorithms. By addressing these challenges through pseudo-labeling, the proposed method improves the labeling efficiency and accuracy, enabling the model to deliver consistent and reliable classifications for various agricultural sensor states. This figure shows the result. Actually, this following figure illustrates the impact of labeling errors on model performance by comparing the manually labeled data with the predicted labels. The top graph shows the manually labeled data with the black sections indicating missing labels and some irrigation segments incorrectly labeled as normal. In the bottom graph, the proposed approach correctly differentiates between normal and irrigation events, emphasizing its potential for automated and accurate labeling. So, the bottom graph shows less black areas, black sections. This is our conclusions. The proposed method for data pre-processing, waveform segmentation, and state classification were evaluated in a smart farming environment and achieved high accuracy in sensor state identification. The model demonstrated an overall accuracy rate of 89% with automated labeling, resulting in a 30% reduction in data processing time. However, the model showed room for improvement in the classification of normal states, suggesting that additional refinement is necessary. Future research may focus on enhancing model generation by collecting data from various agricultural environments and exploring deeper neural network architectures. This is the end of my presentation. Thank you for listening.